All right, on the current internet, one of the problems that we have is that when you register on a site, your identity is with them. So I am Rossman Group on YouTube, I can be LA Rossman on Twitch. My identity is essentially tied to a particular site that can, if they remove my content, can also remove my identity. So one of the problems that we're trying to solve here is coming up with a decentralized way of establishing identity. This person is this person on these websites. He is known or trusted by this particular group of people. So I'd like to introduce the person working on this project called NEOPASS, one of our internal engineers, Harpo.
Cool. Yeah, so I'm going to talk a little bit about two things, both polycentric and NEOPASS, as they kind of both relate to each other. Actually, I should set up my slides here. Cool. Yeah, so start off with the polycentric introduction. So polycentric is a kind of social media project that we've been working on here at FUTO. And the context is mainly kind of broadcast scenarios. So there's a lot of things that are very good at like talking to a small number of people very well. Signal's quite good at that. Matrix is also pretty good at that. And we're kind of focused on, with this project, the case of like, I want to publicly transmit something to a large number of people and like not have to interact with them as part of the process. So in the status quo, everyone's pretty familiar with this, but most social media and kind of broadcast stuff is controlled by a relatively small number of parties on proprietary software with kind of extreme network effects. There's a lot of lock-in. On Twitter, that's just where everyone is. There's millions and millions of people, and even if you get a pretty large interest in switching off, they're just pretty solid. And in a case like Twitter, as opposed to other types of broadcasts, it's kind of like even more difficult in that the most important part for Twitter is probably not even the ability to post content. You can do that on your blog or whatever. Switching where you're posting is quite easy. It's the fact that 100,000 people are following you and you're tied to that one site. So there's kind of like a big alternative to Twitter. Probably the most popular one is Mastodon. And Mastodon has been like pretty wildly successful, especially with the recent Twitter acquisition. But there's kind of a few issues we kind of have with the model that Mastodon has. And one of the core things is kind of how it does federation. So federation is like how email works. It's been very successful, lasted for a long time. You can pick through lots of providers for email, but at the end of the day, who you pick for your email provider kind of matters a lot. They have a lot of authority over you. And if you pick Yahoo Mail or Gmail, and one day they go out of business or decide to stop doing business with you, or change their policies, change their ownership. These types of things, companies get acquired all the time or go out. Your kind of whole identity is kind of tied to this one provider. And Mastodon is the same thing, except it might be even more extreme than email. Like in general, if you use one of the big email providers, kind of within the cabal of providers, you can get through spam filters. You can kind of contact whoever you want. And even if you self-host your own email and you check all the boxes, you have a okay chance of actually getting through. With Mastodon, who you pick to be your provider matters a lot more, and that the providers tend not to like each other very much, and you end up getting this like extreme fragmentation of the network, where instead of there being Mastodon, where I follow you where you are, you follow me where I am, in practice, because the servers are communicating with each other, the entire network is just totally segmented. So if you want to talk to everybody, you're going to have a lot of accounts. And kind of that's a massive pain. And much like email, with Mastodon, it's even worse. Where the servers are relatively small usually. They disappear pretty frequently. They're not around for 10 years. And if your identity was tied up in one of these providers, you're just kind of stuck. Your stuff's gone. If you had followers, sorry, they're gone. Go. And if it's a phone number, maybe you contact a few friends. They have your new number. You're good. You're never getting those 100,000 Twitter followers back. It's just going to take years and years of grinding. They're not going to switch over. And so there is this one project from 2014 that I kind of fell in love with. I thought it was really fantastic when I first heard about it, called Scalpbutt. And what Scalpbutt did is that you kind of had this chain of data where you publish one message and then publish another message and another message, and they all form this chain that was your content. So you'd say, hello, I'm doing good today. This is what I had for lunch. This is my new username. And then you kind of push this data wherever you wanted. And the default model for Scalpbutt was kind of like more wholly friend to friend or peer to peer, where if you're on the same Wi-Fi with people and they were following you, it would automatically sync. Or if you're on the other side of the planet, you could go over the internet. And it was really, really resilient because you didn't really care where the data came from. You just cared that if I'm following you, that I get your stuff. And when you look at the properties this has, this is kind of like the naive properties that has it is really fantastic, and that like, oh, I can publish these messages to all these different servers. I don't really care where I get them. And then, so they had these things called pub nodes, and you'd say, I want to use these 2 pub nodes. You publish them there. One of the pub nodes can go down. It doesn't matter because your data's on the other node. People download it from there. And it's just like really, really incredibly resilient and sovereign. Because once more, because of this, this kind of hash chain thing that they do, the server can't even hide messages. So if you publish 1,000 messages, if the server decides, I don't want clients to get this one, maybe it says something I don't like, then the client sees, oh, the server's hiding it from me. And it's kind of just like cheap to do that. It's like, oh, message 53 is not there. I've got 54 and 52. What's up? And this property of like being able to have a nice server in the cloud distributing all your data on their 40 gigabit network interface, and still be able to still get all the data you want. You're not really losing very much there. You're not really giving them very much authority. They're a service add. They're adding value, and they don't have much ability to take it away except for denial of service. And I really think that's kind of a really, really great model, that if you can use things in the cloud cheaply and efficiently, but have a way where them screwing you over is limited to denial of service, like that's kind of the gold standard. If you can get it. It's hard to get that though with without a lot of work. So Scalpbutt had a lot of drawbacks, and they've kind of slowly improved stuff over time, but a lot of the core stuff is still there. And one of the things that's kind of struggled with is supporting multiple devices. They have some specs for how they might deal with this, but one of the main issues is that there's a feed, and if you have this hash chain, it's a linear sequence, and if you're publishing from multiple devices, well, they don't all have the same data. There has to be more than one feed. So you're basically limited to a single device writing. And most people use social media on their phones, their desktop, their web browser, all over the place. Maybe they have a whole bunch of computers. And so that's kind of just totally unacceptable. And the other issue that I had is that it kind of assumed that you were getting everything in like a big sequence. So you get message 1, 2, 3, you kind of apply the state. And that way you can be very sure that you got everything, but you're probably downloading a lot of stuff that you didn't actually care about to get someone's profile picture, for example. So it kind of had a lot of performance issues and just these basic practicality problems. Now, so the question is, how do we? Is it possible to kind of like take these guarantees that something like Scalpbutt gives you, but then also try to make them a lot more performant and like kind of support multiple devices? So we combine so Polycentric, we're kind of taking, trying to get these guarantees that something like Scalpbutt has, but try to do it in a way that is going to be fast, work on multiple devices, and when someone has 10 million posts, follows 10,000 people, should still work out. So one thing we do to do that is we use a lot of conflict-free replicated data types, and that's a really, really fancy term, but it's used a lot in kind of distributed database technology or text editors, collaborative text editors. Usually collaborative text editors are going to use like something called operational transforms or CRDTs for their collaboration model. And the basic idea is that if you have multiple devices setting the state of something, how do you reconcile that? And CRDTs provide a framework for doing that. In a lot of CRDT literature, there's kind of this problem where it's really easy to make anything conflict-free by just saying, whatever the last thing that happened won. And if you imagine like your Git repo where you didn't have merge conflicts, you just kind of overrode everything. That's kind of like a naive CRDT implementation. And so I kind of think they've gotten maybe a little too hyped up. But the cases that we're using them for are really kind of the simplest possible cases, like a single cell of information. So like, what's my username, what's my description? As these are changed between different devices, what servers do I want to use? There's always kind of like atomic pieces of information without complex structures where there's really only one obvious solution. So they kind of fit really well into the CRDT model. And so because we have multiple devices, we kind of need the CRDTs to resolve conflicts between your devices. The second part is we use this thing called vector clocks. So on each device, vector clocks are kind of this concept of like ordering in distributed systems. And if you have multiple devices, and you're not coordinating with one server or one blockchain or something, one piece of global state, then you have a distributed systems problem. And so one thing we have is that like if I'm publishing a bunch of things on one device, and I publish a bunch of things on another device, naively, these are two disconnected streams of data. And so we need a way to kind of like merge these together so that when people are consuming data, they know that they're connected. Yep. So the vector clock concept is very simple. So on each device, you have a counter. You increment the counter. And so each device alone is kind of like a Scalpbutt feed was originally. But then each message includes a clock. And the clock is the known counter for the other devices. And so when you learn that something on another device, let's say you post something on your phone and you go over to your desktop, assuming you had internet at the time, your desktop sees, oh, my phone published something. And the next time you publish something on your desktop, you go and you increment that clock and include it in your message. And the really nice property of this is that for this kind of like DAG data structure, in the happy case at least, you only need one message. If you get one message from a server, the latest one, you can see everything that exists, the entire state of the DAG, in the happy case, when things were online. So you don't have to like, you don't have to go and look at each device and see like, oh, what's your counter for this one, what's the counter for this one, what's the counter for this one, or how do I find out about other devices? It's just, if the devices know about each other, when I'm writing, I write, and then, I can basically, from that one node, I just look at the counters and say, oh, this is the state of the other writers. And this property is really nice because you can kind of, start consuming data from one server, look at, and then ask another server just for the latest message. And from just that single tiny piece of data, you can see like, oh, is this other server screwing with me or not? Are they hiding devices? Are they, are they super far behind? This kind of stuff. And so this ability to like consume from a server, but then not only be able to kind of use them to deliver the data to you, but also be able to like very, very cheaply check that they're screwing you over is, I think, very important. And because all the events in a system that you publish kind of exist in this larger data structure, we kind of enable that. Naively, you could take each message and publish them independently without like a more complicated data structure. But if you do that, then you don't really know kind of what exists in the full platform. You don't know when you've downloaded everything, and you don't know if servers are hiding things from you. Cool. So we combine a couple of those things. And so the naive case at Polycentric.io that we have right now, and that's just a front end for some servers. The code there is all client side. We have a kind of a microblogging site that's kind of like the first example of this platform. In the future, we're really intending to get into more things like RSS, which I really miss the slow death, or I'm not happy with the slow death of. And I think that microblogging is actually one of the hardest cases for protocols like this. And the main reason I think microblogging is so difficult, you think, oh, it's a small amount of data, it's not a big deal. The reason microblogging is so hard is that when you look at like someone's feed or your own feed, most of the things that you're looking in that feed are lots of different data from lots of different people. So even though it's in a small quantity, if you're scrolling through your Twitter feed, you might have 100 accounts. They all have profile pictures. They all have usernames, descriptions, even the content of their post. And if you have to fetch that from a whole bunch of different locations, designing the protocol to kind of minimize that sync overhead is very important. So trying to do things in single round trips, as a really big example. If you have things like torrents, for Linux ISOs, If you have a large amount of data that never changes, the metadata overhead is very small. You have a hash for the data, you have a way to look up the peers, and then you can download your 1 gigabyte file, your 50 gigabyte file very, very quickly. But the torrent takes half a second to start, because there is that DHT lookup, there is that, and there is that kind of synchronization overhead. And so if you have 100 things in a feed all from different people, you really need a way to kind of like get the guarantees that you're looking for and not have like 90% of your traffic just be like synchronization metadata. It's really easy to, a lot of protocols very easily handle, a lot of peer-to-peer protocols especially very easily handle, large pieces of data that don't change very often. Dealing with small pieces of data that change all the time is much harder. And so there's some other cases that I think a lot of peer-to-peer stuff, and I don't really consider this peer-to-peer because that's not the intended like application of it, but the data model could very well be distributed that way, is that there's a lot of things that are just very hard to do like on your own device or in a trustless way. Examples of that include stuff like full text search. Like naively, this feels like a pretty simple problem, but if you try to, people have like large Elasticsearch clusters in the cloud for a reason. That's because things like full text search are really hard to do on your 2 gigabyte of RAM phone or whatever it is on. It's probably not you're probably not using all that memory for a text index. So we decided to take some compromises on things that are kind of more in that domain, things like search, where instead of like doing big full text search over and trying to compete with your terabyte of RAM Elasticsearch cluster in the cloud, we're going to say that like, okay, like we're going to allow the clients like opt into these providers for things like search, and like these are features that are in the client right now, and then in the UI we kind of like coalesce the results of multiple providers. So like a server will return events to you, and in the UI we surface like, oh, this is the authority that recommended this to me. This is the other authority that recommended this to me, and like at the UI level, this kind of multi-master design I think is really important because just being able to switch between providers, even if it was fairly cheap, I think even that is almost too much of a hump. Like being able to, because you have to switch between them, you have to do your migration. If you can have this multi-master scenario where you can choose multiple people to provide you results at the same time, like the cost of trying out new authorities or new providers is just so much lower. Like there's no commitment costs. And because the cost of switching is so much lower, actors are really much more incentivized to not lower the quality of their service. Yeah. So cool. Yeah. I mean that's the main case for the microblogging. Yeah. We also do stuff like binaries. So like binaries are embedded in messages. Kind of like a torrent. They're split up into chunks and then embedded into the feed, and then you can kind of download them from multiple servers. But the other thing is like also like recommendation engines. Like people kind of like want to choose how things are recommended to them, but it's also very difficult to do that. It's very difficult to do that like all on one device. You kind of have to know about a lot of metadata in order to like use. You can't use like modern machine learning based recommendation engines that are able to like link the semantics of content very easily. It's like, oh, I cared about this topic. I will link to this other topic. That's also very hard to do in a kind of like on-device or trustless way. So, we've also kind of allowed that to be kind of outsourced to providers. So, there's recommendation engines built into the existing server where, multiple servers can run their different recommendation engines. And then in the client, it's like these things were recommended to me based on from this authority, based on these criteria I've set, and they like run concurrently. And if you decide, I don't like these recommendations, you just remove that one. You still have the other 3 that you're using. Again, like when you want to add a new one, it should be very cheap. I think just being able to switch is not enough. So there's the second part of this. I keep wanting to put down the mouse, but there's nowhere to put it. Yeah, so second part of this project is that, so there's this really cool old PGP thing that I think really never took off called Web of Trust. And you'd find someone else's PGP key, like their identity key in the old days, and you'd sign it, and you'd upload that information to a public server, and people could kind of see the relationships between people, like who trusted who. And there are even things like IRC rooms where it's like, you could only go in the IRC room. The bot would only let you in if you're a part of the secret club. And I thought things like that were really cool, because the web of trust model. To clarify, web of trust is like just like me vouching for someone, kind of like in a cryptographic way. And I really liked the model of web of trust because it detaches from authorities. It's a much more like peer-to-peer relationship between like truth. It also implies like there's not a authority that I'm choosing to use. There's like, I can look at like the graph of people that I trust. And there hasn't, at least with the PGP web of trust, there wasn't like a very convenient way to like use this information in a very automated way. Because the tooling around that is kind of difficult, and the tools for exploring it were not very good. Beyond the like basic PGP key management issue, which I think things like Signal have solved at this point, but definitely held back PGP for forever. So an example of this is that, so here's this little like Linktree site that we've built. Familiar with Linktree? It's just like a list of links that people build. So people can take like claims and they publish them in their feed. Like I own this YouTube account, I own this Twitter account. This is my Bitcoin. I can lift 4 plate. And then on the Linktree it'll display like who agrees with that. Linktree is a kind of very simple site, but this is this gets ingested into a polycentric feed, gets rendered by Linktree, and then you can kind of click around and explore, the social relationship. And for things like YouTube accounts or identity recovery in general, and another FUTO project, the video app, an example of this is that like there's a YouTube channel, they want to find like what sovereign identity owns it, but the YouTube client can't go out and crawl like all of the internet. Or all of YouTube to find out who owns what. Or at least even if it was crawling, it can't do that very quickly. So what it can do is it can go and ask. It's like, okay, here's the root of my trust graph. Go find me who owns who made this claim, and find me a path of people that I trust that say that's true. And so when you like ask who owns this YouTube account, the server returns, oh, and this guy owns this YouTube account, here's their identity, and here's the path from your root of trust to that person. So like, let's say, I trust Aaron at FUTO. Aaron's an authority on YouTube validation or something. And then he says, yes, Lewis actually owns this account, and I validated it with my web crawler. Then when you go and ask the server for the proof, I ask who owns this account, and then I give the server who I'm looking for, and who I trust, the root of my trust graph, and then it gives me back, the Lewis's identity, and then it says, okay, Lewis, I trust Aaron, Aaron trusts Lewis, and then it gives me that path. So it returns a path that's probably 4 or 5 elements long. In most cases, it's probably 2 or 3. And then I on the client can see this. Oh yeah, the server actually did that query correctly. The server could choose to do a denial of service, but that's the worst they can do. You can always see that, yes, the server didn't screw me over with this query. So like the space of like, how do we have queries and use like powerful cloud computational resources, but still prevent the servers from screwing us over? And historically that's been difficult, but I think there's a lot of cases like this where clients can very cheaply verify that something expensive was done correctly in kind of a useful way. Yeah, cool. So that's the end of the talk. We have some links up. Also related to this, like we have a little, I'm going to call it an alpha stage app, calling it Harpo so far, and you can kind of, a little Flutter Android app where you can create identities and then make claims. You can scan someone else's claim and validate it, and it will pop up on the link tree. So if someone says they can do X, you can scan it, and then it will pop up on the I'll synchronize in the background through the polycentric stuff. Cool. Yeah, so I jumped over a lot of RAM stuff, but yeah, that's the talk. Any questions? Yeah, so I think in like current identity systems, there's a lot of focus on these things that are like usually called like verifiable credentials, which are usually things like a credential issued by an institution like some university, and that's kind of, and then you're validating to someone that you worked at that university or something. We're much more interested in like getting away from like the model of institutions granting authorities, and more of the tooling around like exploring like more thoroughly social claims. They're not like from an authority. It's like oh, I think this thing is true. I assert this claim. Other people vouch for it. I can visualize that relationship. It's much more about like the publicly explorable information graph than it is like. Yeah, absolutely. That's absolutely in the space of intent and like tooling for managing these kind of complex social structures. I think most of the effort really has gone towards this kind of verifiable credential stuff, which is really great for if you want to like have a login service or something where you want to validate that you worked at some university, then that works pretty well for that. But yeah, this is mostly intended. Most of the intents here are for strictly public relationships. They can be pseudo-anonymous public relationships, but the information, much like the PG Web of Trust, this is stuff where I'm supposed to be able to explore through the system. It's like, oh, this guy said something. Who do they trust that I trust? Oh, that guy seems reputable. There's a lot of things about humans need the information to make these judgments in these kind of complex social situations. If you don't want public information, you don't want people to be able to kind of audit the graph, then stuff like credentials issued by institutions are much better for that. I mean, who owns the keys? That's about it. Okay, yeah, sorry. Yeah, cool.